This video is going to show my attempt at the SACE Mathematical Methods Written Exam 2022, Question Book 2. So I've done questions 1 to 6 in a previous video, and let's jump in here to question 7 at the start of Book 2. So we start off with the graph of y equals x ln x take x, as shown in figure 6. And we're first asked to show that the derivative of that, dy dx, is equal to ln x. So I'm going to do that with some straightforward product rule. Dy dx will be equal to 1 times ln x times the derivative of ln x, which is 1 on x, minus the derivative of x, which is 1. So that gives us ln x plus 1 minus 1, which equals ln x as required. So that's A part 1 done. A part 2 says, hence use an algebraic approach to determine the y-coordinate of the stationary point. So first of all, worth remembering that we're looking for a y-coordinate. Don't want to miss that little bit of information there. And secondly, we're going to use an algebraic approach to find a stationary point. So we'll start with dy dx equal to 0. That'll be when ln x equals 0, which is when x equals 1. And then we need our y-coordinate. Y will be 1 times ln 1 minus 1, which is minus 1. And there's our y-coordinate as required. Now we have a family of functions of the form y equals x ln x take x plus ln kx. So a variation on the function we started off with. And we have a k taking a range of positive values. We're going to generate a table of values here. Let's do that using the graph mode of the calculator. Moving down to a fresh line, I'm going to put my function in x ln x minus x plus, the first function will be ln1 times x. Now the next function will be ln, with the ln1 will change to ln2. I'm going to enter that one while I'm at it using the clip and paste command. So I'm going to arrow up for a moment, then press Shift and 8 for clip, copy the line, move down and Shift and 9 for paste, enter that, Shift and 9, enter that, and Shift and 9 once more. And I now have 4 copies of my function without having to retype any of them. And now that first one, that ln1, will become 2. The next one, it will become 3. And then the last one, change that to a 4. Okay, now my view window is a little bit unclear here, so I'm going to have to, I guess, make a bit of an educated guess. However, the function on the previous page graphed both x and y from roughly -5 to 5 in both x and y. So I'm going to start off with that view window. So there's our 4 functions. Looks like we've got k equals 1, 2, 3, 4, sort of curving upwards as we look from bottom to top. And we should use that to find our y-coordinates of our point A. So I'm going to go gsolve and minimum. That first function is the one from a previous question. We don't want that one. We'd like this one here. y3 is the first one. This is our first function that we've already seen. The y-coordinate is -1, but I'll pop that one down anyway. That was just a little double check that my system was working well. Now gsolve minimum, and we want this one to be y4. That's ln2. That's at -0.5. Now gsolve and minimum again. Once again, arrow down till you've got the right function drawn. That's this one with the ln3x in it. pop that in. That looks like minus a third, and I think you probably can guess what's going to come for the next one, but we'll do it anyway just to be sure. Arrow all the way down to the ln4 term, and lo and behold, the y coordinate minus a quarter. So there's a conjecture being made there. Obviously, looks like y equals minus 1 on k. Hopefully you can see that from the table above. Okay, now it's time to prove or disprove that conjecture. So we're going to take essentially the same approach as before, take a derivative, set it to 0, and solve, and hope to come up with that final result, y equals minus 1 on k. So, first of all, dy on dx, that will be equal to 1 by ln x plus x by 1 on x minus 1, that's the bit we've already seen, plus ln k equals to 0. Therefore, ln x plus ln k equals to 0. So I'm going to use a log law there to obtain ln xk equals to 0. Then I'm going to raise both sides to the power of e. So e to the ln xk is equal to xk, and e to the 0 equals 1. And that means x equals 1 on k, which is looking promising. Now I need the y coordinate. The y coordinate using the original function will be 1 on k by ln 1 on k minus 1 on k plus ln k times 1 on k. So time for a little cleaning up here. 1 on k by ln k to the minus 1. Okay, so we can see our first term has an exponent of minus 1. That means that it can be, using log laws, brought out the front, minus 1 on k ln k minus 1 on k plus 1 on k ln k. And you can see that those first term and that last term are the negatives of one another, and so that equals negative 1 on k. And that was our conjecture proved. Question 8. A question of apricots. Now these are produced on some sort of conveyor belt that can produce perfect, presumably, or imperfect apricots, and the chance of an imperfect one is given to us as 0.15. And we're going to use a binomial distribution to do some calculations involving a random sample of 80 apricots. So the first calculation is a binomial point distribution calculation of exactly 6 out of 80. So off to the statistics menu I go. From distribution I choose binomial, I choose the point distribution, and I choose 6. Well, 6 is the correct current number, 6 out of 80. When the probability of a single imperfect apricoc is 0.15. So my first calculation is 0.0205. Part 2, more than 20 apricocs. That means we want the probability of 21 or greater, or between 21 and 80. So the distribution we want is binomial again, but now we want the cumulative distribution, and we want to go down and start our calculation at 21 out of 80. The number of trials and probability haven't changed, so execute that, and we get a small probability 0.00631. Now this question takes an interesting turn. We're now looking at the probability of an imperfect apricoc being a variable, and that variable is response variable, and the explanatory variable is the speed of the rate of production of apricocs. Obviously, the speed too fast or too slow is going to impact the production. So we're asked to draw a graph on the window provided. Okay, so I'm going to go to graph mode of my calculator, and this time I'm going to be more careful to deselect a couple of functions. Don't want to delete them necessarily. I might want to come back and check results later or something, should I have time in the exam. So I like to leave them in there for now. but my new function is sine of 0.00392 x squared plus e to the negative x. Okay, and the view window we're looking for is exactly the same as the graph we've got, the axes we've got. So it would be wise to set that quite carefully. See the y scale there, 0 to 1, which makes sense seeing as the y represents a probability. Okay, so let's have a look at that one. An interesting beast. So how to draw this accurately? Well, I'd like to get the endpoints right, and I'd like to get that minimum or maximum right. So I'm going to start off with some tracing. I'm going to check where it is at 0. Right, that's up there at 1. That's good to know. Again, that makes sense. And we'll jump to the other end of the scale at 20. Now that's just under 1, so that's virtually the same. And then down here, this point here is going to be critical, so G-solve and minimum. So 3.7 for x and 0.07 for y. So 3.7 for x and 0.07 for y is around about there, drawn on that scale. So now I'm just going to try and fit the graph to it. Looks like it comes down in a concave up sort of a fashion, and then it's clearly got some sort of inflection point. It goes up, and then it seems to have an inflection point quite close to the end, and I think that's probably close enough. Looks like a pretty good draw there. But it's definitely worth getting that minimum in the right point and checking those endpoints. Okay, so let's move on to part C. Part C says, using the function p of x, determine the possible rates that result in a probability of 0.15. So now 0.15 is in fact this position here. Clearly this relationship suggests that there are two possible rates for which that would occur. One of the rates is here and the other rate is there. So I'm going to use an x calculation. So that's a G-solve around the corner, an x calculation, and the y value I'm looking for is the probability 0.15. Calculator picks up the first one, 2.008, so 2.01 to 3 figures, and the second one moving across, 6.15 will be the second value. Now part D asks for the minimum value, and it actually tells us that the minimum probability is 0.0781, and it wants to know the corresponding rate of production. In other words, what is the x value corresponding to that? So I could even use x calculation again, but just to be super safe, I'm going to use the minimum calculation there. We can see the 0.0781 and the 3.576, which looks like 3.58 to me. Again, to 3 significant figures. So there's the x coordinate of our maximum. Now we have a new production rate chosen by the manager, and it's claimed that this will result in the minimum probability of an apricot being imperfect. And they run it for a day and take 80, a random sample of 80, and you get 6 imperfect ones. And now we're asked for a calculation for p hat, the proportion that are imperfect. We're leading into sort of confidence interval territory. First of all, p hat, that will be 6 out of 80. And now we're going to calculate a 90% confidence interval for the proportion of apricots. So that means back to the statistics menu. And we want the interval. This time it's a one proportion interval. We'd like a 90% one, so that's 0.9 for my confidence level. And it's 6 out of 80. And there's my level there. If you feel like it, you could pop that decimal 0.075 up there in E part 1. but what we were looking for there was the bounds for the interval for E part 2. So our interval is 0.0265 less than or equal to P less than or equal to 0.123. Part 3. Using this interval, can we conclude that the manager's claim is false? And the manager's claim was that they had set the line to produce the minimum probability of fruit jar being imperfect. This interval contains the minimum imperfection rate of 0.0781, therefore we cannot conclude that the claim is false. So, lastly, E part 4. Using the interval that we calculated in E part 2 and P of x, the function we were given, find with 90% confidence the upper and lower bounds of the rate. Now, that really means we need to come back to our graph and have a think about what we've discovered. Our confidence interval was between 0.02 and 0.123. So that's somewhere here through to somewhere here on our y-axis. So there's our confidence interval here. Now, what values of x would give such an interval? Well, if we think about our upper bound of that interval, anything between those 2 points would return something that is either 0.123 or less, not as low as 0.02, that won't occur, but anywhere in there will occur based on the confidence interval we've been given. So now we need to know the endpoints of such a thing. So in fact, it's back to our graph. And once again, we need to do an x calculation and to use the value 0.123, and we need to turn those boundaries into an interval for x. So our first point was 2.28, and the second point, found by arrowing right, 5.52. So we've turned our interval for P into an interval for x. Question 9. Question 9 starts us off with a square root function, square root of 8 take x cubed for x less than 2. And we're asked first of all for the derivative, so we'll do that using chain rule. Okay, so the derivative of f dash x will be a half by 8 take x cubed to the power of minus a half multiplied by 0 minus 3x squared. And if we feel like cleaning up a little bit, you can see that the minus a half means it's 8 take x cubed on the bottom, as is the 2, and the top line of that will be minus 3x squared, which is what we were required to show. So that's part A. B part 1. Now we need to show that the normal to the graph has this equation. So first of all we need the derivative value and also the function value at minus 1. So f dashed of minus 1 is equal to minus 3 over 2 square root 9, which equals minus a half, and f of minus 1 equals 3, and based on that the slope of the normal will be equal to 2. And from there we can pretty easily find the equation of the normal using a couple of different methods. I'm going to write the equation as 2x minus y equals 2 by the x coordinate minus 1 by the y coordinate, and that equals minus 5. So we have 2x take y equals minus 5. That's probably the quickest route to home for the equation in that form. Now I need the x coordinate of this normal. That's actually quite easy to find from this one. You can basically, the y term disappears, so you get 2x equals minus 5, so x equals minus 5 over 2. Now we're going to do a general approach to this, where we're going to take that same function but have a normal drawn at the point x equals a. So once again I'm going to start with f dashed a and f of a. So f dashed a is equal to minus 3a squared over 2 by the square root of 8 take a cubed, and therefore the m normal, slope of the normal, will be equal to the negative reciprocal of that, which will be 2 the square root 8 take a cubed all over 3a squared. The point we also need to know is that f of a is equal to square root of 8 take a cubed. So now using that same formulation, but obviously with a few more symbols involved, our normal is 2 by the square root of 8 take a cubed x minus 3a squared y equal to 2 by the square root of 8 take a cubed times by a minus 3a squared times by the square root of 8 take a cubed, which equals 2a minus a squared outside of a common factor of 8 take a cubed. So now therefore the x-intercept, so that's when y equals 0, is equal to 2a take 3a squared root 8 take a cubed all over 2 by the square root of 8 take a cubed. You can definitely see that nice cancelling out of common factors, and so we get 2a over 2, which is a, 3a squared over 2, so that's minus 3 over 2a squared. And I think that was what we were trying to show, so that's our 4 marks earned. So now we have a function where the output is x and the variable, if you like, is a. So now I want to consider, based on my x equals a take 3 over 2a squared, dx on dA, which is equal to 1 take 3 over 2 times by 2a. And we want to find when such a creature is maximised in this case. So we want to set that equal to 0. So that's when 1 take 3a equals to 0, or a equals to a third. Question 10. This involves the service life of an item, and the probability density function is given to us, that complicated looking creature right there, and we're asked to consider when k equals 2. So that gives us a slightly nicer looking function, x over 2 e to the minus x over 2 all squared. And this can be used to model the service life of product A. So we're going to find the probability of it having a service life of 1.5 years or less. So that can be done because it's a probability distribution function. We need to find the area beneath that curve. So 0 to 1.5 are the time span we're interested in. I'm going to do that in run mode of my calculator. That's equal to a probability of 0.430. A part 2, and we're looking at the median lifespan of an object, and that is the probability that it lives between 0 and m years being 0.5. That's the definite interval statement that we've got there. And based on our answer, we can explain why the median must be greater than 0.5 years. As the area under P2 of x from 0 to 1.5 is less than 0.5, the definite integral from 0 to m must go further than 1.5 to capture 0.5 or 50%. Therefore, m is greater than 1.5. B part 1. Now we're asked to show an expression dy and dx for this new function y. So I'm going to do that using the usual laws. So we can clean that up a little bit. So that's as required. Okay, B part 2. We are now thinking about the integral from 0 to m of p of k dx equals a half. In other words, this is the median statement we had before. And we're interested in the value of k such that this median life would be 1.5 years. So in other words, the m value is 1.5. So now we're thinking about the integral from 0 to 1.5 of pk of x equals to a half. Now, the expression that we had previously is in fact the expression for pk of x. So the result we have is in fact the result we need to integrate pk of x, giving us the integral of pk of x being minus e to the minus x over 2 to the power of k. That's from B part 1. Okay, now it's a case of substitute and clean up. Okay, that's looking a little bit better. Now I'm going to keep going and see if I can isolate k here. I'm going to subtract 1 and then take the logs of both sides. So now I'm going to need to, again, cancel those negatives out and take the log of both sides once again. So now I'm going to get k log of 3 over 4 equals the log of 2. So then my final result, need a little more room here, k will be equal to the log of 2 over the log of 3 over 4, and if that's a yucky looking, that's the log of 2 over ln 3 minus ln 4. Either of those things would be the will be an exact value for k. So a bit of a gross looking answer, but given it was the last part of the last question, I think we're going to be happy with that. So that's it, booklet 2 done. Thanks for watching.